I'm Keith Winstein. I'm here in computer science. And my almost entire group showed up to this. This is the first time I've seen them all together, so they will be answering all the questions at the end. So I'm very happy to have questions or interruptions in the middle. Please just go for it. I'm here to tell you about sort of a style of building systems that we've used in our group that has a number of applications. It involves sort of functional programming, but not in the Haskell kind of sense, but just in the idea that it can be helpful to take a sort of mega system and divide it up into sort of small granular pieces. So the message of this talk is that sort of granular functional interfaces to computing resources, reasoning carefully about state, is going to open up new ways of doing things, or new ways of doing existing things and new things that we can do. And I think based on our experience so far, we think there's a pretty strong case that it's worth refactoring sort of the mega modules that we have today, things that people are scared of touching, things like TCP congestion control, or video codecs, or compilers, or machine learning kernels. These are things that people are sort of reluctant to do by themselves, or reluctant to redo. You need an expert to do video codec, or you need an expert to do congestion control. I don't think that's true. I mean, I do these things. I'm just sort of a dilettante. You don't need to be an expert, and you especially don't if you can reason carefully about state, and if the consequences of a mistake are not that bad because there's sort of no side effects. So this ability to sort of save and restore the state of a mega module, save and restore the program state, it's a powerful tool because you can always sort of back up. So I'm going to tell you about 4 systems that we built that sort of demonstrate this idea. So the first is a system for fast interactive video encoding called ExCamera. The second is work we did with Dropbox to recompress all of the JPEGs, hundreds of petabytes of JPEGs that are in the Dropbox distributed file system. The third is a real-time video conferencing system that has, again, one of these purely functional systems. And the fourth, if I have time to get to it, is a system for outsourcing anything to the cloud, sort of make-J1000, 1,000-way parallelism. And each of these uses this functional idea for a different benefit. So in the ExCamera, we have a purely functional video codec that we use to get fine-grained massive parallelism to reduce sort of the end-to-end completion time. In the case of the JPEG recompression, we have a functional JPEG codec, a functional Huffman encoder, DC-predicted Huffman encoder that we use to be able to shard the JPEG files that Dropbox has on a distributed file system. So we can break them up into tiny little pieces that's compatible with their sort of redundancy story, their sharding story. In the case of the video conferencing, the real-time video, we use this functional abstraction to be able to explore an execution path without committing to it. To say, what if we encoded the video at a high quality? What if we encoded the video at a low quality? And then we'll make a decision which one we wanted to do only after the fact. We can sort of rewind state. And in the case of the GG, the massive compilation, we have this abstraction we call a cloud thunk that allows us to outsource sort of any task to the cloud, to these cloud functions for pennies. So you can take a normal sort of Unix pipeline, like a makefile, and infer one of these functional, a Lambda expression really, from it, and then run that with massive parallelism across thousands of workers, or locally, and sort of get the same answer. So there's 4 different benefits from this quasi-functional, functional-ish style. All right, so let's go into the first one, which is the fine-grained parallel video processing. So this was at NSDI last year. The motivation here is that video is really painful to deal with. Who here has maybe kids and you've edited a home movie? Maybe a home movie not about your kids? Yeah, all right, sir. With kids or without? Okay, and how long was the video?
18 minutes.
Okay, and did you edit it or do anything to it in the computer?
Just a little bit.
Okay, and what kind of change did you make? Like a cut or change the colors or?
Just picking pieces and splicing them together.
All right. And then how long did that take end to end to re-render after you did that? Months! That seems crazy.
Re-render.
Yeah, how long did it take just from you making a change for someone else in the world to be able to see that change? Change the video.
No, it seemed to be many times the playtime.
Yeah, and even if it was so-called real time, it would still have taken you like 18 minutes, right?
An 18-minute playback might have taken 3 hours to do whatever had to be done. Now, granted, I don't know what was actually happening. I just know how long. That's how long it took for there was a new file I could look at.
Yeah, so if you think about the things that have made computing like really different, especially things around here like, the Xerox Alto, right? Or like the mother of all demos. Like the amazing thing here was you could take something and make it interactive and see the results immediately. Or Sketchpad. Any of these systems, the interactivity is a powerful thing. I remember McWrite. I mean, McWrite was amazing. It would like the paragraphs would reflow as you typed. Fantastic. Now we have this in a sort of internet collaborative way. We have Google Docs, where if we're looking at the same document and I hit an X, not only do I see the X and the text reflow on my screen, but everybody else sees it too at the same time. The results of making a change are instantly visible. And it's just like sort of the old-fashioned way where you'd like put a pen on a piece of paper and it would like happen immediately. It's like revelatory to have that in the computer context. That's Google Docs. But we don't have this for video. Video is the most popular kind of content on the internet by time spent, by bytes sent. It's the vast majority of content set over the internet. But to manipulate video is a huge pain in the neck. There's no way to have a sort of instant editing and transformation in a collaborative sense of a video. And it would be very nice to have. You could imagine, you have some video. What if you wanted to experiment, apply some filter to the video? That would be nice. Or we could do some analysis, like, instead of skip to the next chapter of the DVD, what if we skip to the next time we see this actor? Be nice. Or how many times does this actor appear? Or can we see a scene that has this actor and this actor together? Can we edit that together? What if you wanted to take an actor and remove them from the movie? That could be nice too. Just like automatically find and replace, like take someone and just take them out. It'd be nice to play with these sorts of transformations in a mech-write type sense, like a sketchpad type sense, like immediately, not have to wait months to re-render an 18-minute video. So if you think about what it would take from a systems perspective to accomplish this, the question would be, in a standard toolbox, can we just put a lot of computers on it? Can we have massive parallelism to be able to apply these video operations just very, very quickly? Bob?
I went up to Apple and took their iMovie course, and I edited something on the Mac using iMovie, and it was stored in iCloud, and I could see it immediately on my phone. So the only difference was that I couldn't.
I'm glad I called on this gentleman and not you to make that example.
Sorry, forget that. Continue.
Well, I think it depends, and we'll see some numerical benchmarks.
For a high-quality movie that's maybe not an iMovie, then it can take many hours.
All right. I mean, you were at Apple, probably with like a high-speed line. We'll show the benchmarks. So the challenge, if you wanted to do this with massive parallelism, is there's sort of two challenges. One is you would need to be able to summon thousands of threads, thousands of cores at once doing this operation. On McWrite, you can hit an X, and it's sort of a 8 kilohertz, megahertz. No, what was it? It was, I don't know, 2 megahertz. Some early Macintosh can reflow the text. What was that? Some number of hertz. Macintosh could reflow the text. And that was considered a major accomplishment at that time, that you could have sort of real-time text reflowing. But to do this with video would take just like many, thousands of computers. And you'd have to be able to summon them only when the user was doing an interactive operation. It would be way too expensive to have these computers just sitting there humming, waiting for you to do something. That's part one. You have to have the available parallelism. The second thing is that how do you get your calculation parallelized enough to make use of that kind of level of resource? So the challenge with video compression is that the finer grained the parallelism, if you try to divide up a video into thousands of tiny pieces, the compression efficiency actually gets worse and worse. So there's sort of a fundamental reason that limits the available parallelism in this task. So that's sort of what our project was about, was addressing those two challenges. So the first is that we made a framework to run these sort of 5,000-way interactive parallel jobs with inter-thread communication on a commercial cloud function service. And number two, we developed a purely functional video codec that allows us to start encoding chunks from midstream. It allows us to have a granularity of parallelism that is finer grained than the dependency boundaries in the video stream. I'll talk about that in a second. So the whole system, we call this ExCamera. So part one is this realization that we had that these cloud function services had an unrealized power. So these are services like AWS Lambda or Google Cloud Functions or Azure Functions. They were intended for sort of event handlers and web microservices, sort of asynchronous tasks where there's a million people with cell phones and maybe occasionally one of them will do something, and then when that happens, one of these functions will get fired off and reply. And the cool benefits is that it's not like you're booting up a virtual machine every time. I mean, I know VMware was a very successful company, but oh boy, this is being videotaped. Anyway, I love VMware. If you think about what should be the abstraction to program the cloud, the idea that you have to have a simulation of an x86 computer with pretending that you have access to the x86 chip and a fake Ethernet card and a fake hard drive and RAM, your own RAM, and that you have to then boot the operating system before you can do a calculation. It seems like there's other abstractions we could think about for how to program the cloud. Because in this case, if to boot up an Amazon virtual machine, it takes a minute or so to boot up. They bill it based on the minute. There's a minimum sort of minute to pay for it. And you'd have to wait like a minute before you could actually do anything, because like Linux is booting up. So the beautiful thing with this new abstraction, this AWS Lambda, is you don't have that. That you can run thousands of threads. It turns out you can run arbitrary Linux executables. We discovered you just upload a static Linux executable, you can run it. And they boot up in less than a second, and the billing is less than a second. So you can imagine an application in your computer that would normally take 1 hour. What if the computer could tell you, what, we can do this locally, it'll take an hour, or I can fire up 3,600 lambdas like that. Each one will run for 1 second. We still get an hour of CPU time. That's going to cost you less than a dime. I mean, that's the economics. I think it's I would pay the 9 cents to save an hour of CPU time, to go from an hour to 1 second. And I think you can imagine any interactive application might be this, like sort of pervasive parallelism for interactive applications. So we built a library to enable this, a library that fires off thousands and thousands of lambdas running a arbitrary sort of executable very, very quickly. So we use a lot of sort of engineering tricks, like we open up a lot of TCP connections and we fire them off at the same time. These are not maybe that intellectually interesting, but we built this framework that that allows us to harness the parallelism of Lambda for these sort of not asynchronously parallel jobs, but burst parallel jobs. We want to come in and say, I want 5,000 lambdas right now. And when we communicated with this to Amazon, we all flew up there, and we had like a hard time communicating with them because we said, they only wanted to give us like 1,000 concurrent lambdas, and we said, can we have many, many more? And they said, well, how many requests per second does your application have? Think of it like an asynchronous thing. And we said, well, most of the time 0. And then occasionally, when the user hits a button, I want as many as you'll give me. I mean, if we could have 1 million, we'd love 1 million. So 1 million per second? Like, no, just 1 million every so often. And that was hard. They really don't like that because they want to have to provision for us. But it's sort of the difference between circuit switching and packet switching. If you think about like booting up VMs for an hour, that's kind of like the AT&T, circa 1955 model, the circuit switching. And what we're asking for is this more packet switched, as an analogy, packet switched interface to the cloud, where we can say, I want 5,000 functions now, I want 3,000 functions now, and they're going to be very short-lived. And this was a challenge when they were starting the internet. When the internet people, Len Kleinrock, called up AT&T and says, I want to be able to send 1 packet. They said, well, sir, there's a 6-minute minimum time. Any telephone call, you can have a telephone call, send whatever you want over, but we're going to bill you for 6 minutes, no matter what you do. That's kind of the world we're in now, where the VMs are going to bill us for a minute, whatever we do, and we want a microsecond. But to have this sort of packet-switched interface to the cloud, it turns out to be very, very powerful. So we were able to get these threads. We can have 5,000 threads starting at the same time. But the challenge is, how do you use 5,000 threads at the same time to compress a video? Because the challenge is, the finer grain the parallelism, the worse the compression efficiency. Let's talk about why that is. What is a video codec? It is 2 modulars, a video encoder and a video decoder, with a contract between them, that you can have raw pictures coming in on the left, raw images off a camera, go into the video encoder, and in the middle there's an opaque bit stream, and they'll go into the decoder, and then on the right side you get some fuzzy version of the pictures on the left. That's the contract between the encoder and the decoder. There's a stream in, a stream of pictures, produces a stream of bits, produces a stream of reconstructed pictures. And the way that the compression can reduce the number of bits from the sort of representation of the raw image is to exploit the correlation between adjacent frames. So if I was taking a video of you right now, the first frame, I would have to send everything I see. I'd have to compress it only using information within the first frame, sort of like just a JPEG picture, just a snapshot. But on the second frame, what the encoder can tell the decoder is, hey, remember that frame I just sent you? It's going to be very similar. So for this little square of the frame, it's going to be exactly the same. And for this little square, it's almost the frame. We just move it down 1 pixel and to the left a ½ pixel. In the next frame, it's almost the same, but I'm going to add this residue to it. And that's how the video compression works, is by exploiting the correlation between the adjacent frames. And that, it's called motion compensated prediction, turns out to be extremely powerful. So in a typical 4K or virtual reality stream, the first frame, the one that stands by itself, is called a key frame. That consumes about 1 megabyte in a typical video. And the second frame and the subsequent frames is 40 times smaller. It's like 25 kilobytes each. So there's a considerable benefit to exploiting this redundancy, the correlation between adjacent frames. And it's the search for those correlations, finding the most concise way to express the difference between adjacent frames, that consumes most of the CPU of a video compression engine. Just finding what is the correlation. These slides are all online. You can, they're not a secret. So the interface that is advertised by commercial video encoders and decoders, whether they're hardware or software, is this sort of stream-to-stream interface. There's an encode function or encode module, and the input is a stream of pictures, and the output is 1 keyframe, that's like 1 megabyte, and then a stream of interframes that make use of the previous frames. And the contract is you can put that same sequence of frames, 1 keyframe and a bunch of interframes, in the decoder and get back a stream of reconstructed pictures. That's the contract. And this, if you can go to Sony and buy a chip that implements this. You can get it in software. No matter how you get it, this is sort of the interface that you get. And the challenge is that it makes it harder to, if you're building a high definition television, this is great. There's a TV station broadcasting a stream of bits. You show it on the screen, it's perfect. But if you're trying to do something interesting that manipulates the state or that parallelizes, this is not the right abstraction. It makes things very challenging. Because let's say we have these 200 frames, we want to encode them. we end up with 1 keyframe and 199 inner frames. No problem. That's sort of 1 megabyte, and then each one of these is 40th of that. What happens if we want to split it into sort of 20 different threads and do it in parallel? Well, thread 1 encodes 10 frames, ends with 1 keyframe and 9 inner frames. At the same time, thread 2 encodes a different 10 frames, ends up with 1 keyframe and 9 inner frames, etc. Each one of these threads ends up contributing an extra megabyte to the compressed result. And so the finer grained the parallelism, the more keyframes we have to insert, the more sort of state refreshes or dependency boundaries in a sort of memory sense. It's a guarantee that this chunk can stand alone. It's not going to depend on anything else. The more memory dependency boundaries we insert, the worse the compression efficiency. So it's not really economical from a compression standpoint to have this finer grained parallelism. So systems like YouTube, for example, they use a granularity of 128 frames, which is about, 5 seconds or so. That's sort of how often they refresh the stream, because more than that, it becomes more expensive. So in order to exploit the parallelism that Lambda and this mu library make available to us, we need a way to start encoding from midstream. We need a way to tell the encoder, you know what, you're encoding this tiny chunk here, but don't start with a keyframe. You need to start with knowledge of the state of the decoder. That you can't just assume it's in some initial state that you get to initialize from scratch, because that's just too expensive. So to do this, we had to be able to define, what do we mean by the state of the decoder? We want to tell the encoder, start encoding from midstream. How do we define midstream? So we implemented a video codec for this Google VP8 format. And we did it in a very rigorous way called explicit state passing style, which is a purely functional style. So we had to define, what does it mean, the state of the decoder? So we defined the video decoder as an automaton, as sort of a finite state transducer. So it starts out in some initial state, and it consumes a keyframe. So this is a coded frame here. This line, this is like bits on the coming over the wire. It consumes a keyframe, and it traverses and enters a new state. This is the new state of the decoder. Then it consumes an interframe. It traverses and enters a new state, consumes interframe, traverses and enters a new state. And every time it takes one of these state transitions, it spits out an image for display on the screen. This is the formal definition of what the video decoder is doing. And each one of these interframes is designed to be applied to a particular source state. So there's an assumption in the interframe that these are this is the information that's available. So that's how we define the video decoder. Here's actually the contents of the state. It's a sort of bunch. It's a few images that have been saved and some probability tables for the arithmetic code. So that's the source state, and then the target state is different images saved and maybe different probability tables, and there's some image that got sent off to the screen. So what we implemented was a purely functional version of a VP8 video coder and decoder. So this is a standards compliant VP8 encoder and decoder, but they're implemented in this way where there's no side effects and it's purely functional. And it's in C++. I don't want to suggest there's no like Haskell smart person stuff here. It's just normal programming, but it's done in a way with no side effects, purely functional. So we have a decode function, and the inputs are the frame it's supposed to be decoding. Those are the compressed bits, but also this explicit object that represents the state that it's in. So that's provided explicitly. And the output is an image for display to the screen, but also the new state for the next time that you're going to run the decoder. So you could decode any video on YouTube this way, any VP8 video on YouTube. It'll work. You just have to keep applying this decode function over and over again and save this state object. And every time you apply the decoder, put the new state object in to the decode function, and then it'll give you a new state object, and then you run that the next time. You sort of thread it through like that. So that's the purely functional decoder for VP8. And then we implemented the corresponding encoder, which takes as explicitly the same state object. This the same kind of state object. There's an image coming off the camera, but we tell the encoder, this is the state of the decoder that you can assume that it's in. And it produces a compressed frame, an interframe that relies on the decoder having been in that state. This is a purely functional, no side effects implementation of one step of a video encoder. And finally, we implemented a transform that modifies compressed frames into a different version of the same compressed frame. We call this rebase. So it takes an interframe that was intended for one state, and it modifies it to be applicable to a slightly different state, still targeting the same image off the camera. So this is kind of like in Git in software development. If I have some state of my software repository and I want to make a whole bunch of changes, I can hire a bunch of people on Upwork and ask 1,000 different people to make 1,000 different changes in parallel. And they all make a change on the same version of the repository, and I end up with 100 Git commits all dependent on the same repository state. So now what do I need to do? Well, rebase was the answer I was looking for. Yeah, rebase was Hope for answer. I need to rebase these on top of each other to produce a linear history. Well, I need to sort of cherry pick them and turn these commits that were intended for one history, one state of the repository, to be applicable to a different state, a slightly different state, so that they can have a sort of linear history. So that's the third operation. So we do that for these video frames, and the hope here is that the rebase operation will be pretty cheap, because once you already know what's in the compressed frame and you know the temporal correlations, you know that this car in this frame is the same as this car in this frame, you already have that information. So you just have to sort of recode these residues, but it's a small change. So the algorithm we have here is to try and do as much as possible in parallel, and then do that rebasing, which is a sort of linear step, do that at the end in serial, but that's supposed to be a cheap thing. So we have the parallel step where we encode the tiny independent chunks, and then a serial step where we erase the extra keyframes and we thread it all together, so we end up with a playable video that doesn't have a lot of keyframes, even though it was encoded mostly in fine-grained parallelism. So I'll show you what that looks like. Step one, we have all these separate threads. We've got 5,000 threads running on AWS Lambda all at the same time, and each one downloads a few frames, let's say 6 frames of raw video from the camera, ExCamera. And then it encodes them the sort of simple way, using a production video encoder from Google. We encode them, and we end up with 1 keyframe and then 5 interframes in each chunk. So now we have a playable video. You could play this if you want. You start here, you play this, then you throw that state away, start here, play this, throw that state away, start here, play this. It'll play, it'll just be very big, because every one of those keyframes is like an extra megabyte. So the question is, can we now rewrite those keyframes and turn them into interframes? So we're going to do that. We're going to have our encoder start from midstream. So we figure out what is the exiting state of every chunk here, the final state, and we, in parallel, send that to the next thread. And then we have the next thread encode the first image in terms of that exiting state, instead of in terms of this sort of initial blank state, in terms of the exiting state. So it looks like that. I'll go back once. This is what we had. This is what we end up with. So we run our encode function. That's the one time that function is going to get invoked to encode the first image in terms of the exiting state of the previous chunk. And now all we have to do is we don't quite have a playable video now, because we play here, we're going to end up here. Now we're stuck. There's no way to get up to here. So what we now have to do is just rebase. These states are very similar, so we're just going to rebase this chunk to be applicable to this state, like that. And then we do it again, and we do it again. That's a serial step. So most of the work is done in parallel, but that rebase happens at the end. So that's the algorithm. And there's a few different variations. We can run different numbers of frames in each chunk, and we can rebase and stitch different numbers of chunks together. And I'll show you an evaluation here. So this is looking just at the compression efficiency. So the question is, as the bit rate goes up, how good does the quality go up? So this is a standard metric, structural similarity. And so we can see the best encoder you can get. This is Google's VPX encoder with 1 thread, no parallelism. As the bit rate goes up, definitely the quality goes up. And Google's multi-threaded encoder, this is with the maximum parallelism that they have, there's a compromise, because we end up not being able to predict across these boundaries. It's still pretty good, but this is the best Google can do in a sort of multi-threaded way. So now let's look at the dumb hyperparallel way, where we just encode separate 6-frame chunks, but we don't stitch them together. So that looks like this. This is not that good. And now the question is, what if we encode the separate 6-frame chunks, but then we stitch 16 of them together in a row? So we eliminate 15 keyframes. That looks like this. So we're able to get almost the same compression efficiency as a function of bitrate, almost the same quality as a function of bitrate as the Google encoder, using this much finer grained parallelism, just the 1/4 of a second chunks. So that's the compression efficiency. Now let's talk about how long it takes. So that best of breed encoder takes 7.5 hours. So we took a 15-minute video, 4K video, uploaded it. Well, we tried to encode it in various ways. So this 15-minute 4K video, the best ever encoder takes 7.5 hours to encode, and that's on a fast Intel machine. And the super parallel encoder from Google takes 2.5 hours. We also looked at, what if you sort of had access to all the parallelism you can imagine? I mean, Google's got a ton of computers, so let's just upload the video to YouTube and let them encode it. And that takes 37 minutes for their fastest encoder, but that's only using this parallelism of every 128 frames. So the question is, what if we use 20 times more parallelism? We're going from 128 frames, we have 6-frame chunks, and it ends up about 14 times faster. So we're 20x the parallelism, about 14x the speed compared with sort of end-to-end YouTube. And this is sort of to make the video end-to-end available on the web, so the whole pipeline. So that's the sort of speed comparison. So the lessons here, number one, these lambdas can be used for a lot more than sort of asynchronous event handlers. They can be used for these burst parallel tasks. I mean, it's sort of like a supercomputer that you can access, paying by the 10th of a second. It's a very powerful abstraction. And I think it's going to allow us to parallelize all kinds of jobs if we can express the job in a fine-grained parallel way, which even with considerable overhead is going to have a huge benefit. Taking things that take an hour and being able to do them in 1 second is just so powerful. I mean, that's sort of the lesson of all interactive computing. So I don't think it's going to be just video editing and home movies, but any sort of filter or 3D artists. The people at DreamWorks, when they want to see, should I move the light on Shrek's head from here to here, it takes something like 4 hours to see the result of that. They have a very parallel operation. They could probably render all of the movie in 4 hours, but that's because they have a CPU for each frame. But that doesn't help you if you're trying to make an artistic decision about where should the light be on this particular frame. So being able to do that with massive parallelism, or any sort of compilation, which I'll talk about later if we have time, or interactive machine learning, or data visualization, or any database query, or Google search, or genomics, all of these applications, I believe, may have a button on your screen that says, OK, I'll do this calculation. You press this button, it could take an hour. Or press this one button, I'll do it in 1 second. It'll cost you 9 cents. I think we're sort of back to the 60s, where computing is going to be a sort of build by the millisecond utility, but we'll have access to just like so much powerful parallelism in the cloud if we can treat application state as a first-class object, and if we can divide up our tasks with sufficient parallelism. So that's sort of part one. I'm going to move on if there's no questions. Yes, sir.
Point was that from the keyframe, each interframe is significantly smaller.
Yes.
When you get to the rebase, it seems like what you're doing is building a special kind of interframe that goes from what you had produced to what you need to start from, which may not be as dense as the interframes you were computing earlier.
Well, that operation has access to the original image. So we really just throw this keyframe away and we make a fresh interframe.
Make that fresh interframe working from both ends, both what you started with after several steps of compression and what you need to start with as something that would be ideally your keyframe for the next. You're throwing away a keyframe, but you need to exactly reproduce that keyframe in order to have the starting point that the next stage is all expect.
Well, it's not exact is the sort of secret here. It's not the when we rebase is how we patch up those residue differences. So it's not exact. Yeah, to do it exactly would be very expensive.
And does that intermediate frame then have the same compression ratio as the interframes that you would have with a conventional technique?
It's a hard question to answer that precisely because that interframe is encoded with our encoder, which he wrote, and the original interframe was encoded with Google's encoder. So to answer that question fairly would probably require more work. Yes, sir.
Go back to that illustration. So the way you have it drawn here, and I could be completely wrong, it looks to me like it's a synchronous serial string.
Well, OK, so this part is parallel. You mean ultimately we end up with a playable video. So yeah, it is a. The decoder will download this and just play it in order.
So if thread 2 needs an interframe from thread 1 to start, thread 2, how does thread 2 start before thread 1 completes?
Well, so this part happens in parallel, and then this part happens in parallel, where they share their exiting state with the next thread, and then this part happens in parallel. All right, why don't we move on and we can, I can show you, we have another graph on this that might help you at the end. All right, so the second application of these sorts of techniques was something we did with Dropbox, where they have a whole bunch of JPEGs in Dropbox. This was also at NSDI last year. So Dropbox has roughly 1 exabyte of other people's data in it. And all these things have been uploaded to Dropbox. And the median number of times that they get downloaded, anyone want to guess? 0 is the answer. Most files uploaded are never downloaded. Most YouTube videos are never watched. Most people never tweet. The internet is mostly just a ghost town. So yes, but they nonetheless have an exabyte of people's data, which they have pledged to not lose. And about a third, well, more than a third of it, like 40%, was JPEG files, people's pictures. A lot of these were taken with mobile cameras. So if you imagine that's roughly 300 petabytes-ish of JPEG files, the company is very incentivized to want to save back-end space. So you can imagine how would they do that? And you could think, well, JPEG was standardized in 1989, and when people use JPEG, they only use techniques that were not patented in 1989. So maybe there's something over the last 30 years of compression, 29 years of compression that have improved that we can use to recompress these JPEG files. Now, the simplest way to do it would just be to decode the JPEG file and then recompress it into some more modern image format like HEIF or whatever. But you can't do that because people would be pretty angry if you change the contents of their files in this distributed file system. You can't have someone has their JPEG in a Git repository and you just go and change it and they say, well, now my hashes don't match. You say, oh, no, sir, it's better. That doesn't fly in the file system business. So you have to keep the exact same content of the file. But nonetheless, if you look at how JPEG works, there's pixels coming in, and then there's a lossless transform that's applied. There's a discrete cosine transform. That's basically lossless. But then those coefficients, the DCT coefficients, are divided by a quantizer. And that's the lossy step. It's an integer division. So they're divided and then rounded off to the nearest integer. That's the lossy step. And then at the bottom of this pancake, those coefficients are just written out using a Huffman code. And that's a totally lossless operation. So the theory would be, let's just strip off the bottom of the pancake, decode those coefficients. We're not going to change anything about the lossy part, but we'll just re-encode the same coefficients using a smarter code, maybe an arithmetic code, something like that. So people have done this. And we can look at how well these techniques work. So here we're seeing the compression savings as the compression savings go up. And here we'll see the speed of the corresponding decompressor. So the best algorithms are sort of up and to the right. And you can look, one thing you can do is just rearrange the coefficients to make them more compressible. So if you put numbers that are similar closer together, JPEG has this DC predicted Huffman code, so it's better compression if the similar numbers are together. So this is one thing you can do, JPEG rescan, that's really good, but not so good compression efficiency. You can also change the Huffman code for an arithmetic code. So arithmetic codes were known in the 80s, but they were patented, so nobody uses them. But we can use them now. So you can imagine re-encoding them, as there's a tool that does that. So that has not as good decompression speed, but the compression efficiency is better. And anytime you have an arithmetic code, really what matters is how good can you predict whether the next bit is a 1 or a 0. Because the way it works, if I know for certainty that the next bit is a 1, and it is a 1, it consumes 0 bits in the output. And if I know for certainty it's a 1 and it turns out to be a 0, like a Trump election or something like that no one expected, then it's like infinite bits in the output. That's sort of the Faustian bargain you make with these arithmetic codes. The better that you can predict, this is sort of a machine learning problem, the better you can predict the probability of the next bit being a 0 or 1, the better savings you can get when you're right. And then if you want to be crazy about it, like this German guy, you can do the world's most complicated arithmetic code. You can take all the coefficients of the file, this global operation, resort them in the most compressible order, and then have a huge model, like 100,000 parameters in your machine learned model to predict whether the next bit is going to be a 1 or a 0, and then use an arithmetic code based on that probability model to compress them. So this gets about 23% compression efficiency, very slow to decode, because it takes all these sort of global operations. The challenge here is that in the file system context, you cannot have a global operation on a file, because no part of the system, of this distributed file system, ever sees a file at once. Instead, these files are divided up into small blocks, content-addressed blocks, and they're stored redundantly. So if you upload a JPEG file to any of these services, Dropbox and Google, they're all sort of similar. Well, I don't know that. I'm guessing. Anyway, I can tell you about Dropbox. But the files are split up into separate pieces, and each piece is content addressed. So it's addressed by the hash of its contents, which means that they don't have to store duplicates. If two people both upload a chunk that's all zeros, they only have to store that once. So when your computer wants to retrieve a file from Dropbox, it goes out to separate backend file servers, and it asks for different chunks, different blocks of the file. So you can imagine it would be nice to be able to compress them and turn each chunk into a correspondingly compressed chunk. We call this Lepton. A Lepton file representing a certain number of bytes of the original file. But then when the client downloads it, it ends up getting the original JPEG piece of the original file. This is the way it would have to work. Because anything else, either if somebody has to know the whole JPEG file at once, that's not going to work. And also, if you want to send the Lepton file down to the client, that's not going to work, because there's no way to sort of upgrade every client in the world, and they have like 1 million clients. And so it has to be sort of this transparent compression operating at the file system chunk level on each backend file server, because that's where they have the redundancy. So the challenge with this is that you have to be able to take the file and store and decode it in these independent chunks. And these chunks can start at any byte offset, because they're sort of up to the file system people. They're not up to me. I mean, the files have already been sort of pre-chunked. And you have to be able to achieve like good decoding speed. So people have like 100 megabit per second connections to the internet. You can't suddenly make the whole Dropbox 10 times slower. They won't like that, even if they never download the files. When they do download, they're going to notice. And it's very important not to lose data. So you have to make sure that this whole system is immune to any sort of pathological or adversarial input. Every time the program changes, it was very important that it runs successfully and identically on 1 billion files, each compiled with 3 different compilers. And it has to be completely deterministic. Because the thing that terrifies an organization like this is that they'll compress a file, someone will upload a file, they'll compress it, they'll double check at that time and decompress it, make sure they get the same thing, they'll store it, and then 6 months later, the same user will try and download the file, they'll decompress it, and the hash will not match anymore. And then they're in trouble. So it's that non-determinism that they're very terrified by. If there's just a bug when they go to compress it and then they decompress it again, if they don't get the same answer, then they can write me a nasty email and say, you know, we were never going to work with Stanford again, we're very unhappy with you. But if they store the file because it worked once and then it never works again, then they've lost someone's data. So it has to be deterministic, which is not something that our programming languages really are very good at ensuring. It's very hard to avoid non-determinism. There's so many ways to get non-determinism in a normal sort of programming language. All right. So the question is, how does the file server, when the client goes to the backend file servers and requests pieces of a JPEG file, the file server has to decode it from our crazy format, which is fine. But then the hard part is it has to re-encode it in this JPEG format. And how does a file server start re-encoding from midstream? That's sort of the challenge. The same challenge as before. It has to be able to re-encode from midstream. However, it turns out to be much, much easier than before because JPEG is really simple. So it's so easy to be sort of scared of it. Oh, it's this 1980s thing. It's a Huffman code. It's very complicated. It turns out if you just sort of play with it, it's not that complicated. So we formulated this JPEG encoder, this DC predicted Huffman encoder, in explicit state passing style. And then we implemented it as a pure function with no side effects. So there's a state object that evolves byte by byte as it's writing out the JPEG file. And then once you have that state object, you can resume from anywhere, even in the middle of a Huffman code word. So a Huffman code word could be 17 bits. You want to be able to resume anywhere because the byte boundary might not be lined up with it. So it turns out you can get that state down to 16 bytes. It's not that complicated. It's the partial Huffman code word. It's the one you were in the middle of sending. You say, well, I've sent 3 bits of my 7-bit code word, so you've got 4 bits left over. That's one thing you have to save. And then it's DC predicted, so you have to save the prior DC values. It turns out to be not that complicated. And you can just, once it's functional, you can have a regression test and say, well, give me the hardest file you have, and I'll just try freezing the state at every byte boundary and then resuming from there. And I'll see if I get identical results. And we got that down to 16 bytes. So once you have this sort of ability to back up and experiment with different choices, it turns out to be a lot of fun to make. So we ended up doing this, and we used this ability to break the file up and start encoding from midstream. We use it for 2 purposes. One is to comply with these file system block boundaries. And the second is just to have parallelism even within a single file server. We may as well just split it up into 8 pieces so that we can decode it more quickly. So I'll show you the benefit of just the second choice, just decoding a single block. Here again is the 3 techniques, and here's the software that we published. So this is sort of open source software. It ends up being almost the same compression efficiency as the crazy German guy. Not quite, but almost. But it's 9 times faster, and that's within a single block. So if you have 2 blocks, it's 18 times faster. So this is the fun. Well, so it's encoded 150 billion files. It's 200 petabytes have been encoded, saved like 46 petabytes. They have a cluster running this program. This one program consumes 300 kilowatts continuously, compressing the back catalog. And they suspected a bug at one point, and they turned it off. And the power consumption only dropped to by half. So the program there's a cluster running that only runs the program that consumes 300 kilowatts, but half of that is just like the blinky lights on the front of the machine. You consume half the power whether you're running the program or not. So for people who actually make computers, this seems stupid. But anyway, it incentivizes them to keep my program running all the time. So the lesson here is that a little bit of functional programming can go a very long way. We're talking about 16 bytes of state here. This is not that hard to keep track of. But by having it, you can do all kinds of crazy things, like 23% compression of hundreds of petabytes of JPEG files fitting within an existing context where you don't control the boundaries. All right? OK, so great. So that's how a company and a different company made money. OK, so let's talk about some more work we did where there's yet another benefit of functional programming, or it's functional style of implementation, where we were able to make a video conferencing program that works better than ones like Skype or Facetime or Hangouts or WebRTC. And the advantage here is that by having a functional abstraction to the video codec, we can explore the consequences of an execution path. We can follow an execution path a little bit, and if we don't like it, we can abandon it. So we don't have to commit to an execution path just to try it out. We get that again by this sort of purely functional abstraction. So this is going to appear in this year's NSDI. And the observation here is that if you try video conferencing, Skype or FaceTime or Hangouts or Chrome WebRTC, over any sort of network where there's uncertainty or variability, People do this? Anyone ever video conference like when you're in the car or anything like that? No one tries it. Have you tried it, Devin? How well did it work?
Not so great.
What happened?
I cut out.
Yeah. Yeah. Anyone else had this experience? People just don't even try. I got on this topic actually originally when I was in grad school, and my advisor says, I don't think this is a good topic. You know, it's a very well studied topic, Skype and Facetime and Hangouts. And then he says, I have to go home and see my kids today, so we're going to have to continue this conversation over video conference. So he's Skyping home through the streets of Boston with his phone up like this, and it was terrible. No one could understand. And then he's like, okay, maybe you know, it is a good topic to work on. So one of the problems here, in our opinion, is that the way these programs are architected is that companies are scared to sort of do it all in-house. So video codecs are thought to be a specialized thing. You have to buy a chip to do it, and companies outsource that. So when I was in, in grad school, we developed a transport protocol, which is a way of sending data over the internet and a way of estimating the available capacity of the network. And we thought our transport protocol was pretty cool, and we went to Skype and we said, you should use it. It'll be better than Skype. And they said, well, it doesn't really work that way because we don't make the whole system. Our video codec, don't tell anybody, but we license it from Google. Because at that time, Skype was using VP8. So they say, we don't have the flexibility to combine these things in the way you're talking about. We have sort of separate modules. We have a transfer protocol that we make, and we have a video codec that Google makes, and they interface sort of at arm's length. It's a modular system, and it's, in my opinion, it's too modular, or the boundaries between the modules is just not good. Yes, sir?
Video conferencing and everything worked perfectly until Microsoft bought them.
Well, we don't have data on that. This project's only about 2 years old. What was that? No, I don't I don't know. So this is sort of the current architecture that these two components. But we went to Google and we said, okay, you should use this transfer protocol because you make the video codec. And they say, well, yes, but as it turns out, this is on Hangouts. We don't make the whole transfer protocol. We license that from a company called Video. And then later I was on a panel discussion with the chief scientist of Video, and I complained, and she said, oh, no, Google, we didn't give them our good stuff. We just gave them our consumer stuff. You have to be testing our good stuff. So it's very hard to pin these companies down. But ultimately, I believe the problem is that the architecture is too arm's length. So what happens is that the transfer protocol can tell the encoder what sort of bit rate to target. There's an estimate that the network has a certain bit rate. And these systems started sort of in the world of ATM, where you could reserve an isochronous delivery channel over the network and get a particular bit rate. And this tell the encoder, okay, we've reserved 1 megabit per second, encode at that. And then the encoder, based on that, chooses its encoding parameters. It chooses a frame rate, it chooses a quantizer, some quality setting. And then the transport protocol is stuck, sending whatever the encoder created, even if it overshoots or undershoots that capacity. The problem is that the capacity on the internet can change. It's not like ATM. You don't have provision capacity. It can change. And there's sort of too much latency between the encoder and the transfer protocol to match the encoder's, the data that the encoder is generating to the varying capacity of the network. So what actually happens in WebRTC, for example, if the encoder generates a frame that's too big, they don't have a way to not send it. So the network thinks that the transfer protocol thinks the network can accommodate a frame of a certain size. The encoder, for whatever reason, generates a frame that's too big, which can happen all the time. These encoders on a single frame basis, it's very hard to target a particular compressed frame size a priori, because you don't know what the correlation is going to be between a frame and the previous frame until you sort of try to compress it. So it's on a single frame basis very easy to overshoot or undershoot. And that's why these encoders specify an average bit rate. They don't tell you a particular frame is going to be a particular size. Nonetheless, for the most part, the transfer protocol just has to send it. Even if it knows at that time that the frame is too big, it still has to send it. And then it screws up the network. It causes congestion. And then they enter what they call, they say, well, now I know that I've screwed up the network, so I'm going to pause the input to the encoder. I'm not going to encode any more frames for a while. I'm going to wait for this congestion to clear. But it would have been much better to pause the output from the encoder, for the transfer protocol to tell the encoder, you know what, you made a frame that's too big. I'm not going to send it. I'm going to throw that away. I'm not going to send that and screw up the network. Try again, encode another frame that'll be smaller, send that one. That would be nice. But once the encoder has encoded a frame, it's gone through a state transition. Remember, that's the interface, encode a stream. The encoder has the state inside itself. There's no way to tell it to sort of back up. So that's what we wanted to explore. If you can explore an execution path without committing to it, what sort of benefits can you realize? So if you build a combined algorithm with one control loop, so there's not sort of a frame rate and a bit rate. These are not separate. There's one rate. And every time through the control loop, we call the transfer protocol function, we call the video codec function. We say, what's the capacity of the network? What size should the frame be? We go just one control loop. Can we build an application where the video transmissions better match the varying capacity of the network? So in the system, we have a video-aware congestion control scheme, a video-aware transport protocol scheme, and we have a sort of network-aware video codec. And they're fused together to sort of better match the evolving capacity. So the way we do this is, it's the same video codec that I showed you in the first part of the talk. There's that decode given state, encode given state. That's the interface. We don't use the rebase. And every time we go through this control loop, there's an estimate from the network, from the transfer protocol, about what is the size that the frame should be. How big do we think the network can accommodate right now? Because if you send more than that, you can cause packet loss or you can cause a queue to accumulate. You don't want either of those to happen. So there's some estimate about the size. And every iteration of the control loop, it would be very nice if we could tell the codec, you know what, we think the next frame should be 17 kilobytes, so make it exactly 17 kilobytes. There's no way that codecs can't do that, because to do that you have to sort of try to compress it and see how big it ends up being. So instead we beat this with trying multiple options. So we tell the encoder, you know what, try a higher quality version than the one you just sent, and try a lower quality version of the same frame. So we have one state that we assume the decoder is at. We ask the encoder to try higher quality encoding and lower quality encoding, both based on the same state. And then the transfer protocol has options, because it can look at what the actual size is that it wants the frame to be, and it can look at what the sizes turned out to be that it's actually gotten from the encoder. You know, there's a frame that's 20 kilobytes, there's a frame that's 10 kilobytes. So it has three options. It can send the 20 kilobyte version, it can send the 10 kilobyte version, or if it doesn't think the network's ready, it can just say, you know what, we're not going to do it. We're going to take a mulligan. We're not going to send a frame at all. And we'll just go through the control loop another time. We'll encode a new frame, whatever next comes off the camera. But we're going to base it on still the same state of the decoder. It's as if nothing ever happened. It's just a total do-over. So this turns out to be a very powerful capability to have, to explore execution states of the encoder without committing to any of them. Because it means the frame rate of the system is totally dynamic. It's not 60 frames per second. It's not 10 frames per second. We send a frame or don't send a frame at any moment based on whether we think the network can accommodate it. So when the network gets good, we can send more frames. If the network's bad, we just skip more frames. But ultimately, there's no time evolution, like a frame rate that's evolving and forces the computer to send a frame when it doesn't want to. You never send a frame unless the network is ready. All right, so how do we evaluate this? We were very proud of the evaluation test bed, which the people in this room built. This is the first time this appears to have ever been done, is that we have a comparative evaluation of different black box video compression system, video conferencing systems in a sort of codec agnostic way. So the goal here was to have a totally reproducible video that we stream, reproducible video conference, a reproducible network conditions that we test over, and we want to run the unmodified versions of the system under test. So I don't want to be changing Skype or Facetime or Hangouts or WebRTC. I want to run them unmodified, and of course our system, and we'll just see how well they do. And the target metrics are the sort of standard quality of experience metrics. The delay, what is the delay between when something happens at the sender and the first time you see it at the receiver? And the quality, which is the same structural similarity metric. So here's the actual system. So we have a computer with a very cool and expensive Blackmagic HDMI input-output card. So we have a we have a real video conference that some of our colleagues generously provided. So these are them pretending to have a video conference. What did you tell them to do? You say pretend to have a video conference? OK, so it's a pretend real video conference, actual people. And then it's 60 frames per second, high definition. And then we put on each frame, we put a barcode identifying exactly which frame it is. And this is a big barcode. Every dot there is 16 pixels across. And the goal here is that the barcode will survive any sort of lossy video compression and video transmission. So we barcode every frame, 60 frames per second, and we play it outside this computer at this very rigorously time-stamped way. So this card has a hardware timestamp, so it can tell us exactly, sub-millisecond granularity, when did that frame leave the HDMI port. And then it goes into this box, which is made by a company in downtown Palo Alto, that converts HDMI into a pretend webcam. So HDMI comes in here, and what comes out is a USB port that pretends to be a webcam. And you can plug that USB port into a Mac running Facetime, or a PC running Skype, or a Linux machine running Hangouts, or our system, and they all appear to be a webcam. So these computers think they're getting webcam input, but they're really getting our reproducible test video with barcodes on it. And it's all time-stamped to the millisecond. So then that computer sends video running Skype or whatever it's running, however it wants, over a time-varying network whose trace of sort of variations in capacity is synchronized to the video. And then it goes to a receiver computer, also running the unmodified Skype or Facetime or Hangouts. We full screen the window on the receiver computer, and it comes out the HDMI port on that computer back into the same fancy card that the video came out of, where it gets time-stamped on receipt by the hardware clock and that same PCIe card on the same time base that the video was sent at. And then we just recognize the barcode, which is really big, so we match up the corresponding frames. When we sent that frame, when we receive the same frame, then we can get the frame-by-frame delay of every single frame. And once we have the corresponding frames, we can measure the quality, the structural similarity between what we sent and what we received. So that's the benchmark. So let's look at some network measurements, and then we'll look at some video measurements. So here's a network measurement. We just look at what happens when the network gets worse for a while, and then it gets better for a while. So this shaded region is the network's capacity. So it just gets worse, and then it gets better. And we can see how the different transport algorithms behind these schemes follow or don't follow the network's varying capacity. So Salsify is the red line. That's our scheme. So you can see it sort of follows the network's capacity. When it gets bad, we're sending really bad video, or maybe no video at all. And when it gets good, we sort of resume. And you can look at Skype and WebRTC. They're a little more stubborn. So Skype tries to send at a particular rate, and it continues trying to send at that rate even when the network has fallen out beneath it. And there used to be a mentality, well, there still is a mentality, that you want to have slowly varying video quality. It's not good to change the user's video quality too rapidly. And it makes sense that maybe you don't want to increase the quality too rapidly because it could fall away again. But it does not work to try and slowly decrease the quality if the network has already fallen out beneath you. Because all you're doing by sending faster than the network can accommodate is causing packet loss or building up a queue. It ultimately does not serve the quality of the user. There's no reason to slow down the decrease. Because you can look at what happens, and Skype actually recovers here. WebRTC gets totally confused, and it's in its like bad network mode, and it's just not sending anything at all. So we can also look at a video metric of delay. Here, every dot here is a frame of video. And we can see the delay between when it's sent and when it's received. So WebRTC is sending, Salsify is sending basically constant delay. And then when the network is bad, the delay spikes up for a bit and then recovers pretty quickly. That's the red line. Skype doesn't slow down fast enough. It builds up a big delay, and it takes a while to recover. And WebRTC starts out with a big delay. It spikes, and then it gets totally confused and sends a bunch of frames here. Then there's nothing for about 8 seconds. It sends one frame here, and then nothing for a while, because it's in this bad network mode. This is Skype in Chrome 62. OK, it's a recent Chrome. So we can also look at the quality metrics, and we see them here. So here we see the video delay is on the x-axis, and the best delay is, again, on the right side. We flip the x-axis, and the quality structural similarity is here on the y-axis. So the best schemes will be up and to the right. So here's Salsify, which gets the best video quality and the best delay of any of the sort of conventional schemes over a Verizon LTE type network trace. So I'm not sure that, it surprised me that we're able to get better quality. So many of these schemes are using very fancy video compression formats, VP9 SVC or H.264. A video encoder written by one graduate student in 3 months for an outdated format is able to beat all of these schemes on a video compression metric of structural similarity. That suggests that improvement in video codecs are not that helpful in this context. The difference between VP8 and VP9 SVC, or one grad student versus Google, it didn't cause Google to win this one. But improvements in video systems must have considerable low-hanging fruit if one research group building a better system with a better architecture can outperform the best video codecs. So this is over a Verizon trace. Here's an AT&T trace. Again, best quality and comparable delay to Skype. Here's over a T-Mobile trace. Again, best quality, lowest delay. So I think this mode where we think of a video codec as a specialized thing that operates on streams, and we don't ask for the ability to introspect on its state, or not even to inspect the state, but just to be able to save and restore the state. This is not a world you want to be in. Every component in your system, you want to be able to save and restore the state and talk about the state. Because to treat these components as something foreign that you just have to live with, oh, the codec produced too big a frame, well, we have to send it anyway. You don't get good results. You have to be able to reason about state and integrate these control loops in order to get good quality results. I think that's the lesson there. That's a third benefit of the sort of functional programming paradigm. All right, I'll take questions there, and then we can move on to the fun demo. Yes?
Are you using the same, are you and Google using the same video quality metric?
Well, I mean, this graph is using structural similarity as the video quality metric.
Right, but I guess my question is, is Google possibly using a different quality metrics that they would do better on, like one that takes human factors into account and isn't just like signal processing?
Well, I think it's possible. I mean, this work is funded by Google, I should say. So I think if they had we go over there and we presented this work at Google. I think if they had a better metric for us, they would tell us. I mean, what did they say when we? They seem to believe SSIM is a reasonable metric. They do care about compatibility with hardware codecs. I mean, to implement this, you need the interface to the codec to be able to save and restore the state. So Hangouts is supposed to work on sort of every cell phone in the world. I think that is one limitation. There's a major limitation of the scheme is that you need the interface with the codec. All right. So I'll just quickly talk about the last thing we're doing, which is trying to outsource sort of any. Do I have it here? Sort of outsource any calculation to the cloud. So take just a universal abstraction to take anything you might do on your computer, on your laptop, and extend it to the cloud. So these sort of laptop extension workloads. And we talked about this a little bit, but what are the things you spend CPU time on your computer? It's like compilation, maybe searching for things, maybe analysis. John analyzed 20 terabytes of Antarctica radar images. How long did that take? Yeah, it took a long time. So anything interesting that you want to do with a computer that could take a long time, what if there were sort of common interchange format, an intermediate representation for the cloud, kind of like the LLVM-IR or like Halide, some way of declaratively specifying a Lambda expression for the calculation that you want to do, and then let's talk about evaluating it, maybe locally, but maybe also across 10,000 Lambdas or 10,000 OpenWhisks, or maybe if everything's purely functional and reproducible, maybe we just sort of throw it up on Reddit and let anyone evaluate the functions. Anyone could volunteer. That was maybe too much for this group. Anyway, anyone could evaluate the functions and give us the answer. As long as it's deterministic, it doesn't really matter who's doing it. It doesn't have to be Amazon. It could be anybody. So that's the idea. So we've done this sort of for compilation and for video compression. So I want to see if we can get the demo to work. So we have the system here. So here I have FFmpeg, which is a video compression tool. It takes about 10 minutes to compile. So I think if I just did make-j8, let's see here. All right, so here's what it normally looks like. Just takes a long. I'm not going to make you sit here for 10. Well, it's 10 minutes on a single core, so it'd take like. Well, this is a 4-core machine. Anyway, I'm not going to make you sit for that. But that's what compiling looks like. What if instead we try and take this make file and infer a Lambda expression, infer a very big expression of nested functions that have to be evaluated to ultimately produce a program called FFmpeg. So that's basically what we've built. And the thing that we didn't want to do is have to learn anything about make files, because that's super unpleasant. You can imagine we're going to read the make file and we're going to infer the functional dependencies between stages. And that's not so much fun because no one really even likes make files. I mean, there's people who do Ninja and people who do Bazel and people who do CMake. You don't want to sort of tie to a particular make file or something like that. So the question is, can we infer or reverse engineer the functional dependencies of one of these Unixy tasks just by sort of pretending to actually do it? So that's what we built. Should we do the hello world? Let's try the hello world. Okay, so here we have a hello world program. Just see the last time I gave this talk. Hi, EE380. Okay, so here we've got hello world, and I could compile it to hello like that. What if we fake do it? What if we pretend to do it? So we have a program here called GG. So our system is called GG. It's the Stanford Builder. George Goodman is the Freemason who built Stanford University. You can see his name in the main quad. So we have the Stanford Builder. We're going to infer the functional dependencies of a compilation process. So I'm just going to prepend this GG infer here to the command line. And it pretends to compile. But it doesn't really compile. It runs it through something we call model substitution. So we run not the real GCC, we run a model of GCC. And this model has to figure out for every stage in the real compilation. So what we just did here was we pre-processed it, we compiled it, we assembled it, and we linked it to produce this file called hello. For every step, we need to be able to model the functional dependencies of that step. So what does it take to pre-process a file? What do you have to know? You need to know what's in the file. You need to know what's in all the header files that the file includes. And that's most of it. You also need to know what is the preprocessor itself. So if you had that information, what's in hello.c, what is in the preprocessor itself, which version are you using, and then what's in all the header files that it's going to include, or at least which header files does it want to include, that would be enough. That's the functional dependencies. And then you could run that anywhere. What does it take to compile a file? You basically just need the preprocessed input and the compiler, and you run the compiler on the preprocessed input, and that produces the assembly output. And then to assemble a file, you need the assembly output and the assembler. You run the assembler on the compiled output, the assembled output, compiled output, and that produces the object file. So what is this term when we take a program and we apply it to data? That's sort of like eval and apply, right? It's like the list community coming back that we heard about earlier. You can't keep us down. Except this is all just C++. It's not. There's no smart people who are involved in this. So what we can see is the output here. It did write a file called hello, but if we look at it, it's not a real thing. It's a thunk. It is a memorialization of what would have to happen if we ever wanted to actually evaluate the output of that step of functions. So we have a hash here, and we can describe it. And what it tells us is that, OK, there's some function that's going to be applied. The executable is called GCC. And here's the exact hash of that executable. So it's totally content addressed. And then here are the data dependencies. Here are the arguments to the function. One is the contents of GCC. Here's some helper program that GCC depends on. Here's the linker. Here is an anonymous dependency that is another thunk. So what is happening here? This is the last step. We're linking it. So the inputs to the linker are the object file and then the linker itself. And the linker runs on the object file. So the object file is not known at this stage because that's also a functional dependency. This is like f of g of h, et cetera. So this is the output of an intermediate stage in the compilation. And we can look at this thunk too. GG describe this guy. So this is the assembly step. So we have the assembler in here, and the input is the compiled output, and the in assembly, and the output is the object file, et cetera. So we have this chain of dependencies. So that's for hello world, but we can run any sort of build process, and as long as everything hard that it tries to do has a model, we can extract a functional tree, a Lambda expression, from what was a very messy and complicated thing. So let's try it with FFmpeg. I'll make clean here. I hope this works. So we'll do a gg infer make. So this is going to run a whole bunch of GCCs. I should have done it with the time. Let's do it. We'll do it with the time. Try to impress you. OK, time. So this is going to run a whole bunch of compiles and links and preprocessors and all kinds of crazy things. But it doesn't really run them. It just runs the models. And that took 3.8 seconds. And at the end, we have something called FFmpeg. But it's just a thunk. And if I wanted to force the thunk, I could run this shell script. And it would compile in Lambda in the cloud, and then produce an executable, and then download the executable, and then run it. So let's do that. And I'm going to do it explicitly so we can see the UI. We'll see if it works. We don't have the best failure handling right now, but it's purely functional. So if it crashes, we just Control-C and do it again. It picks up from where it left off. So it's a bonus. OK, well, how parallel do you want this to be? 200 or 200? OK, here we go. All right, ready? OK, done 3. Oh, OK, there we go. OK, so we see here, here's 200 pending lambdas. Here's the number that are done. There's 5,000 separate functions to compute. And we've spent 6 cents, 7 cents, 8 cents. We're 90% done. All right, now we get down to the final linking stage. This is kind of Amdahl's law coming to bite us. Last one. Come on. Oh! I wish this had worked in my last, more important venue for giving this talk. Anyway, it worked. And we can run it. And hey, it's FFmpeg, just built in the cloud. So that was a deterministic evaluation of a Lambda expression that had 5,180 sub-expressions, totally functional. And that Lambda expression was learned by running the makefile through this model substitution, where every stage, we didn't run the real stage, we ran a fake version that sort of inferred what to do. So we believe, at least I hope, that this kind of abstraction can allow people to outsource anything you might do on your laptop if you can divide it into lots of tiny pieces and write it out in this sort of JSON format, which is not that hard, outsource it to Lambda or OpenWhisk or a family of EC2 machines, or maybe even crazy people on Reddit. Because once it's all deterministic, you can run the calculation anywhere. It's deterministic and content addressed. And you can even share the memoization cache. So when I've evaluated this function to be something else, in fact, let's just try that. Make clean, gg infer make-j. OK, and now let's gg force -j200 ss fmpeg. OK, ready? See, it was memoized. So all those 5,180 sub-expressions have a name, they have a hash, and we've memoized that thunk, when forced, evaluates to a certain output. So we can resolve the whole thing from the cache. So no two people ever have to evaluate the same function twice. So this is kind of the world I want to live in, where you don't depend on Amazon or IBM or anyone to be honest. You express your things in functional format, and then you can outsource them to anyone you want. And it's totally interactive and fast, and you can run 5,000 jobs in like 10 seconds. So ultimately, I believe that sort of granular functional interfaces to computing resources, this is the way we got to go. Anything that works on streams or anything that's big and scary, we got to blow that up. The point of being a hacker is to not be scared anymore. And if you divide things into small enough pieces, no one is scary. It is worth refactoring these interfaces to the codec or the compiler or TCP or machine learning, whatever we're most sort of scared of or is most grody. Some neural network, blow it up, functions. And the ability to sort of save and restore program state, it turns out to be a very powerful tool. Even if you can't understand what's in the state, just being able to do that, very powerful. I showed you that for video encoding, where the benefit of the functional style was parallelizing in tiny little pieces. I showed it for Lepton, where the benefit is being able to match the arbitrary boundaries of a distributed file system. I showed it to you for Salsify, where it's being able to explore an execution path without committing to it, so we can match the video codecs generated bitstream to the network's varying capacity. And I showed it for hopefully everything, sort of compilation of everything in the cloud for pennies. Thank you very much.